Hello, I'm Alan Rosas, and in this video, I'm going to be solving two exercises from section 10.3 of James Stewart's Calculus Early Transcendentals. So the first one is one from 15 to 20, and it's number 20 specifically. And these problems read, identify the curve by finding a Cartesian equation for the curve. And we will also do number 26 from problems 21 through 26. These read, find a polar equation for the curve represented by the given Cartesian equation. So in the first problem, we're given something in polar form, and we want to convert it into Cartesian form, whereas in the other problem, we're given something in Cartesian form, and we want to convert it to polar form. All right, so where do we begin? The key thing to being able to solve both of these problems is to remember how to convert between Cartesian coordinates and polar coordinates. So you might remember that the Cartesian coordinates x, y are related to the polar coordinates r theta by these equations here. So x is r cosine theta and y is r sine theta. How do we make use of these? Well, the first thing that catches my eye when I see this equation is this sine of 2 theta here. And generally speaking, let me make this a note for everyone. If you see sine 2 theta or cosine 2 theta, use double angle identities to convert them into sine thetas and cosine thetas. So let me remind everyone what these identities say. So the double angle identity for sine 2 theta says sine of 2 theta is equal to 2 sine theta cosine theta, whereas the one for cosine says that cosine 2 theta is cosine squared theta minus sine squared theta. The first of these is going to be useful for us because if we take our polar equation here and we replace the sine of 2 theta with this guy here, we get the equation r squared times 2 sine theta cosine theta equals 1. And what's really useful here is that now that we have only a sine theta and a cosine theta, we can go back to these equations here and solve them for cosine theta and sine theta to then plug them in back here. So first off, cosine theta from this equation up here, dividing both sides by r gives us that cosine theta is x over r. And similarly, sine theta is going to be y over r. And if we plug these in to this equation here, what we get is r squared times 2 times, well, sine theta is y over r, and cosine theta is x over r, and all of this is equal to 1. What's really neat now is that we can actually cancel all the factors of r. So here we have 2 factors of r, and then the denominators here we have 2. So this equation simplifies to 2yx equals 1. And because x here cannot be 0, because if we plug in x equals 0, we get that 0 equals 1, which is a contradiction, we're allowed to divide by x, and 2x, in fact, to get that y is 1 over 2x. Some of you may recognize this as the equation for a hyperbola. And as a quick reminder, for these kinds of hyperbolas, the ones that where you solve for y, they're going to look generally like this. If the coefficients, so here, with our hyperbola, this one half is positive. If our coefficient was negative instead, it would look like this instead. But here we have that the 1/2 is positive, and so we get the black curve instead. Okay, now let's do problem 26. So once again, we're in reverse here. So we're given the Cartesian equation, and we want to find the polar equation for this curve. Once again, we will need that x is r cosine theta and y equals r sine theta. And so just plugging these in for x and y, we're going to get r cosine theta squared minus r sine theta squared is equal to 4. Or if we factor out the r squared and clean up a bit, r squared times this is equal to 4. Now, technically, this is already a polar equation, so we could call it quits here and just be done with it. But on an exam, you might be expected to simplify wherever possible, and here we can actually do that. So you might recognize this expression here as the thing that appears for the double angle identity for cosine, which I'll remind you is this. And so what we see is that this expression here, well, this is just cosine 2 theta. And so our equation actually simplifies to r squared times the cosine of 2 theta is equal to 4. And this is good enough. We don't need to simplify this further. If I were a professor and I were to give this as an exam problem, I would count this as the correct solution for that problem. Or if you want to take it a step further, so you can actually divide by cosine 2 theta to get that r squared is equal to 4 secant 2 theta. And note that we can actually divide by cosine 2 theta here because it can't be 0 in this equation. If it were, then the left side would become 0, and we would get 0 equals 4, which is impossible. Either one of these is fine. I like this one better personally because it's in terms of cosine, and I just have a bias for cosine over secants, but it's up to you how you decide to write this for an exam. All right, that's it for this video. If you have any questions or comments, please feel free to leave a comment, and I will see you all in the next video.